Bernhard Riemann reshaped the mathematical landscape by building bridges between unrelated worlds. On this map, calculus, geometry, and number theory are no longer isolated territories, but parts of a unified whole, mastered by one mind in a life of only 39 years. Bernhard Riemann saw mathematics as a unified landscape, where a single mind could bridge calculus, geometry, and prime numbers. In a life of 39 years, he produced just 8 major papers, yet each acted like a seismic shift, rewriting the foundations of how we measure space and infinity. Historically, calculus was built on shaky foundations. While we can easily calculate areas for polygons, curved functions create a nightmare for measurement. A rigid ruler simply cannot follow a curve, leaving a gap of uncertainty. Riemann realized we needed a better way to measure this blue area. To measure the exact area under a curve, we divide it into rectangles. With just a few blocks, the red gaps represent a significant error in our calculation. But as we slice the area into thinner and thinner rectangles, that error vanishes into the limit, revealing an exact value of 1/3. Does this work for all curves? Whether it's smooth curves or jagged step functions, Riemann's approach is universal. By making rectangles infinitely thin, we can measure virtually anything on a flat plane. But this raises a new question. What if the surface itself was curved? Euclidean geometry was born on a flat plane, where triangle angles always sum to 180 degrees. But Riemann asked, what if the ground itself is curved? On a sphere, the rules of shape change entirely. Lines bow, and angles can exceed the limits of the flat world. Riemann recognized that in curved space, the shortest path, the geodesic, isn't a straight chord, but a curve along the surface. He unified this using the metric tensor, a mathematical grid acting as a local ruler for every point. By redefining distance, Riemann provided the essential language for Einstein to describe how mass curves the very fabric of spacetime. 60 years after Riemann, Einstein realized that gravity isn't a force, but the curvature of spacetime itself. This grid deforming around a massive star shows that objects aren't being pulled. They're simply following the straightest possible paths through warped geometry. Even our GPS satellites must account for this by correcting a 38 microsecond daily drift. To map complex numbers, we extend the real number line with a perpendicular imaginary axis. Every coordinate pairs a real and imaginary value, allowing functions to bloom into these undulating landscapes. Riemann surfaces solve multi-valued functions by stacking complex plane copies into a single three-dimensional object. Connecting these sheets allows one input to have multiple outputs without contradiction, turning abstract algebra into tangible geometry. The square root map reveals the true beauty of Riemann surfaces. Because a root like 4 has both positive and negative results, the function is multi-valued. Riemann solved this confusion by stacking 2 copies of the complex plane together. Traveling around the origin shifts you to the other sheet automatically. Here, geometry is the algebra, making invisible properties tangible through three-dimensional space. Prime numbers are the atoms of mathematics, seemingly scattered at random. While their individual appearances defy prediction, a hidden density emerges at scale. This curve reveals that primes follow a precise statistical law, a harmony linking these discrete numbers to the continuous world of calculus. Euler found a profound link between arithmetic and primes through the zeta function. When we sum these reciprocal squares, the result converges to pi squared over 6. This bridge connects addition to multiplication, allowing Riemann to extend this map into the complex plane. Riemann's masterwork began by taking Euler's zeta function and daring to treat the variable as a complex number. By extending it beyond the real axis, the function spreads across the plane through analytic continuation. This reveals a pole where the sum explodes, but more importantly, it unearths a series of critical zeros that hold the secret to the primes. The zeros of the zeta function act as a hidden frequency controlling the prime numbers. While the logarithmic integral provides a smooth estimate, it misses the local turbulence of the primes. These correction waves, derived from the locations of the zeros, refine that estimate until it aligns with the actual staircase of prime counts. But where exactly are these music-making zeros? The Riemann hypothesis suggests that every single one lives on this critical line. We've verified trillions of them, and not once has a zero stepped out of line. It remains the greatest unsolved puzzle in math, worth a $1 million prize. Riemann's work serves as a master map of the mathematical landscape. By connecting calculus, geometry, and primes through a single framework, he proved no field exists in isolation. Though he published only 8 papers, they still guide us toward the deepest undiscovered truths in our universe.